So I want to try and get people used to the closed string B model. It's a little bit complicated. There's a little bit of algebra involved, so I suppose we'll plan to try and go through it slowly. So let me just, we'll start by introducing the algebra of what is called polyvector fields, which are a bit like differential forms. So we're just going to work locally on C3. And we're going to say that the algebra of polyvector fields on C3 is built from, we take the just functions and we adjoin some fermionic variables. And I hope the indexing convention is clear. So the index without a bar refers to the holomorphic directions, and those with the bar refers to the anti-holomorphic directions. So there's a total of 6 fermionic variables. We let PVKL be the space where there are K betas and L BZ bars. So an element here has an expansion, some mu I1, IK, I bar 1, I bar L, eta I1, eta IK, BZ bar, R1, BZ bar, I bar L. So an element of the space is just a certain kind of tensor, but because we're on a complex manifold, the tangent space splits into 2 pieces, the holomorphic and anti-holomorphic. So we can have just slightly more general kinds of tensors. And because these are fermionic variables, this thing here is anti-symmetric in both sets of indices. So there's some operators we like to write down in this space. E bar, which goes from PVKL to EVKL plus 1. That's defined by the formula. D bar is sum. D bar of mu is sum of d mu dz bar I wedge. Sum dz bar I wedge d mu. Right, so we differentiate this coefficient and we add on another dz bar. And del and this is given by the formula del of mu sum e eta I e I mu. So we differentiate coefficient with respect to z and remove an e. Okay, so this is just some useful terminology. So C So last time we talked about Beltrami differentials, which control deformations of complex structure. These are beta in PV11, and we can write beta as some beta I bar j, beta j, ez I bar. Then, as we saw last time, this is the thing which describes an infinitesimal deformation of the complex structure, and it changes what it means for a function to be holomorphic. And we saw last time as well that there was some, this thing will satisfy some equations which mean that the deformed geometry will still be Calabi-Yau. The equations they have a nice presentation in this notation. So the first equation is that del beta is 0. And the second equation is that del bar beta plus half del beta squared is equal to 0. So this equation is a kind of a divergence-free condition, and this is the integrability equation that guarantees there are enough holomorphic functions. Okay, so so the closed string B model has a Lagrangian where the fields include a Beltrami differential satisfying this equation, and the equations in motion includes this equation. So let me write down the formula for this Lagrangian. I'll focus on the part where there's only a Beltrami differential, and I'll introduce the other fields momentarily. So the most important field is beta here, satisfying del beta equals 0, and the Lagrangian is slightly annoyingly non-local, but let me write the formula and then we discuss why it's annoying. Del bar beta wedge del inverse of beta plus 1/6 integral beta wedge. Okay. So let's look at these two terms. So this term is totally fine. Beta is in PV11. So if I wedge over this out 3 times, this is in PV33, which is the same as scalars, because we're antisymmetric in each set of index. We have 3 I indexes and 3 I bar indices. So this is something I can integrate. Here, because I'm assuming del beta is 0, this is not part of the equations of motion, this is just kind of an a priori assumption. It's very reasonable to assume that I can write it as a del of something else. This is in PV21, and this guy is in PV12. So when I wedge them together, I still get something in PB33, which is a scalar that I can integrate. So that, yeah, I mean, the first thing you see, like when I first saw this Lagrangian, I was just baffled by the appearance of del inverse, and it is quite confusing. Let me try to explain how to understand this better. Wow. So the closed string B model this corresponds to certain fields in type 2B on C3, something like this, on some 10-dimensional geometry. I don't want to go into details of how this localization works, so I'm just introducing this for people who are familiar with string theory. And what does beta correspond to? Beta corresponds to, well, it comes from the Ramond-Ramond fields, but it's not a field, it's the field strength. So it's certain components the or phi form field strength. Now, inverse beta should correspond to something like the or Ramond-Ramond 4 form. So once you recognize that this guy should naturally be thought of as a field strength for something perhaps more primitive, it's not crazy to write del inverse. And you can also think about the problem we're having here, that like we have a fundamental field which is forced to satisfy an equation, actually also happens in type 2B string theory, not in type 2A, but only in type 2B. In type 2B, you can't really declare that the Ramond-Ramond 4 form is a fundamental object because the Ramond-Ramond 5 form has to be solved with dual. So the real fundamental thing is this 5 form, but then you can't write the Lagrangian just in terms of the 5 form because you have to impose the condition that it's closed. That's not part of the equations of motion, it's just constraint on the fields. So that condition is entirely analogous to this point there.
So in practice, do you use some kind of Poincare or something to write beta as
yeah.
I see, and then, so you don't really invert down there. I mean, effectively, you just use the.
Yeah, I mean, you could also say that, like in practice, even though the kinetic term is badly behaved, when you write down the propagator to do perturbation theory, the first thing you do is invert the kinetic term. Now, the inverse of that kinetic term is perfectly fine. Because it looks like del bar inverse. Is that perfectly reasonable? So you can write down Feynman diagrams and perturbation theory with absolutely no problems. Okay, any other questions? Maybe I can try to briefly relate this to ordinary Einstein gravity in a very kind of hand-wavy way. So if we choose some reference scalar metric on C3, then we can raise and lower indices, right? Then we can write eta I, upper I gets sent to eta lower I bar. We can raise and lower indices, but it changes an I to an I bar because it's scalar. And then the Beltrami differential, beta I bar I, can be written as this kind of 2-index tensor. So you can argue that this guy is 6 of the 21 components of a metric. I take a metric has di bar j bar, di bar j, di j, and these components are a Beltrami differential. So when we're studying this 6-dimensional theory, it's like we're studying 6-dimensional gravity, except we're only really allowing ourselves to fluctuate some of the components. This is the kind of thing that happens if we're looking at a supersymmetric piece of 6-dimensional gravity, where supersymmetry fixes these pieces, and where there's only some pieces left. So this is super hand maybe. Some of you won't even write anything. The other thing you can see is that yeah, there.
So does this extend to that action being something covariant? I mean, can you give me something meaningful metric? Is it like
I believe so, but I don't know how to prove it. So I think that this action is a certain localization of 0,1 supergravity in 6 dimensions. But I can't prove it because supergravity is a big mess.
Right.
So the other thing you can notice is that if you have if X is a compact Gravia threefold, then every complex structure on X has a compatible Ricci flat metric by Yau's theorem. So on a compact manifold, so every solution of the equations of motion of the B model, well, this is an integrable complex structure. It comes from actual solution of Einstein equation. By throwing away some components of the metric. So what you drop from going to here, from here to here, is the Kähler metric, because if I have a particular complex manifold, can have several different Kähler metrics, each of which gives rise to a solution of sense equation. Okay, so I like to believe that when we're studying this kind of topological B model with our expansive theory, we are studying like a little toy piece of actual gravity. Maybe that's a fantasy. Yeah.
How can we drive this Lagrangian that you wrote?
Yeah, it's a. I expect that the way it was derived in the paper of BCOV was that they knew what the equations of motion had to be, and they guessed it. I think you can derive it from string field theory. This term, if you compute the B model vertex, and I put in a total string field there, you really will get this term. So this term, you can also kind of slightly hand-wavingly convince yourself that the propagator associated to this is related to what you get from the annulus in string field theory.
Yeah, but action of string field theory for type 2B has infinite number of terms, right?
Yes.
So just truncate this.
Oh, I mean, how do you derive it from type 2B?
Yes. There's a twist of type 2B string field theory and then drive this action.
Yes. Well, if you're a little more careful and you write down, like honestly, what the string field theory, what you get from actual string field theory, then you get an infinite tower of fields and an infinite number of terms, of which this is the lowest. But the other terms are not that interesting. You know? Okay, so let's try and describe, so we want to study holography. So I want to try and describe how you do the back reaction of a brain. I mean, like, there's lots of fun things you can do with this stuff, and I'm not sure where we can go. Oh. It's also fun to study the Green-Schwarz mechanism in this setting. So consider C inside of C3. Last time we saw that there was some certain chiral algebra living on this brain. Now we want to study how this brain changes the geometry on the complement. So if we put a brain and brains here, we get a term in the Lagrangian where I have what we had before, then plus n times minus, doesn't matter, integral over C del inverse of beta. So why does this make sense? So we notice that this is a 2-1 form, which looks like, say, mu I bar jk bc bar I eta j, okay? Now I can hit this with epsilon ijk to turn it into a 1-1 form. Epsilon I k k u r L. L. This is a 1-1 form, which I then can integrate. Okay, so why is this a reasonable thing? So to understand why this is what we should be doing, we should think about this analogy with physical type 2B string. We know from the work of Vafa and other people that the B model is related to type 2B in 10 dimensions. And the brain wrapping C becomes a D3 brain. And beta becomes the self-dual biform field strength. Now, when we couple a D3 brain, what we do is we integrate the Riemann-Roman 4 form over the world volume of that brain. While the Riemann-Roman 4 form, d of it is this guy. So integral over the D3 of Riemann-Roman 4 form looks like the integral of del of kind of d inverse the Riemann-Roman 5 form. That's what we're doing. Yeah.
Sorry, this del inverse beta thing, that's a 1-1 form. So that'd be like a star del inverse beta? Because that's, wait. I'm just confused about this epsilon thing you did, basically.
About this going to 2B? Oh, this thing here?
Yeah.
Sorry, so del inverse beta is, I shouldn't have said form. That was my mistake. It's 2-1 polyvector field.
Yeah.
So I can, this is in wedge 2 of the tangent bundle, which is the same as the cotangent bundle. So that epsilon ijk thing is doing. It's changing this eta and eta into a dz. Make sense? You think about the representations of SU3.
Yeah.
This is like the exterior square of the fundamental. And the exterior square of the fundamental is isomorphic to the anti-fundamental because we're in dimension 3. You can also think about the cross product. Make sense?
I think so, yeah.
Okay, so again, by analogy, it seems this is like very analogous to what we would do in type 2B string theory. So we will just proclaim that this is the right thing to do. And now let's solve the equations of motion in the presence of the brain. And solving those equations will give us the back reaction of the brain. So we just vary beta, and we find del inverse d bar beta plus a half beta squared is equal to the delta function on the location of the brane times del inverse. Now I hit both sides with del inverse, find that d bar beta plus a half del beta squared is equal to the delta function on C. And now we can solve this equation quite explicitly. So we choose coordinates so that we choose coordinates z, w1, w2, so that the brane is at the location wi equals 0. And a solution is given by, sorry, I forgot the factor of n. Beta is okay, so I claim this is a solution. So the first thing to see why it's a solution is to notice that beta is del z times something, and del z wedge del z is 0. So beta wedge beta is 0. So this term of the equation is gone. We just have to check that d bar of it is a delta function.
Is it overall n?
Yes. There's also some factors of pi. So we need to check. Bar beta is a delta function with wi 0. Okay, so this is I'm sure some people have seen this kind of thing before, but I don't know how to do these computations. Oh, wait. I don't know. I'm easily amused. I find these kind of fun. Well, so the first thing is to notice, well, if it's going to be, if d bar of it is a delta function, then d bar of it is going to be 0 away from the locus with the wi is equal to 0. So you can calculate explicitly that d bar of this is equal to 0 away from the origin. And you just do this by differentiating this expression. And it's important that it's a power of 4 there. A power is not 4 will not give you 0. And then, therefore, d bar of this thing is equal to the sum of the delta functions plus derivatives So, dimensional analysis, that the derivatives of the delta function have different dimension than the delta function. That tells us derivatives can't appear. The coefficient of the delta function is given by the integral over a ball and this integral you can just compute. It's some multiple of pi. I forgot the d bar. D bar, I mean, the clever way to compute it is use Stokes' theorem. It's the same as the integral over the boundary. When I integrate over the boundary, I can drop this term. This is the unit sphere. And then I'm just taking this, that's just the standard volume form of the sphere. It's the volume of the free sphere. Okay, so great. So now we've solved the equation for the back reaction. But it's not clear we've learned anything. We just have this funny Beltrami differential. So what we're supposed to do is figure out what are the holomorphic functions on this space. So how does this guy deform the geometry? So we search for functions f, z, and wy which satisfy e bar f plus epsilon n times epsilon ij So this is the new equation. This is, once we deform, this is the equation telling us we have a holomorphic function in the new complex structure. When we get this extra thing. So you can play around a little bit. Well, let's see. The first thing we notice is that if I just take the functions w1 and w2, this term won't contribute because the z derivative of them is 0. So f equals wy solves this equation. But there's two more solutions. So you might think at first sight that you could take z and add a correction term to it to make it solve this equation, but you can't. You can, however, take w1z or w2z and add a correction term make it solve the equation. So the other two solutions look like the following. W1 Z plus N I forget the formula. Sorry about that. Yeah, minus N. Something like this. So if you are a here, you can, what you have to check is that d bar of this cancels W1 times that expression there, which you can check. I'll call this guy U1, this guy U2. So now we found there's 4 holomorphic functions. However, of course, it's a 3-dimensional manifold, so there should be some relation. And U2 W1 minus U1 W2. Let's look at that. But do U2 W1, I get this W1 W2Z. Here I'll also get a W1 W2Z, so they'll cancel. But here I'll get N W1 squared over W squared plus N W2 squared over W squared. So that's N. So these guys satisfy the relations to define this manifold. So the algorithm is we solve the equation with a Beltrami differential. We look for the new holomorphic functions, and those are coordinates on my new manifold. And I found that I have 4 coordinate functions which satisfy this relation. So the conclusion is that the back reactor geometry is going to be the manifold of 2 by 2 matrices. Of determinant equals 1. Or determinant equals n. I feel like I'm going very slow. Any questions? Now, if we were doing this in the usual type 2b setting, once we study the back reaction to geometry, we wouldn't find something with very much symmetry. It certainly wouldn't have symmetry reflecting the conformal symmetry on the space-time. But here, we notice that it has the conformal symmetry of the spacetime built into it. As SL2 times SL2 symmetry from right and left multiplication so in particular, we take one of these guys to be the conformal symmetry of the spacetime. This is equal to conformal symmetry times the Ore symmetry. So we didn't have to do any near horizon limit to get here, so it's much easier than the usual holographic situation. We also notice that this manifold is it's naturally isomorphic to hyperbolic 3 space times a 3 sphere. So this is the usual like Euclidean version of ADS3 times S3. So this is the right kind of setting for holography, where one SL2 acts here and the other SL2 acts here. Okay, I'm kind of out of things to say today. So maybe next time we can study, so now we know what the back reactor geometry is, we can try to study the large N CFT next time, the holographic dual, the local operators, then we can move on to more exotic examples. So any questions? Or?
Is there any sense in which this does capture the holography from physical stream perspective? I mean, is this somehow localizing?
Yeah, we think so. We think that this is an ADS3 times S3 inside ADS5 times S5, and which the physical string localizes.
I see.
And so you, on the CFT side, the two-dimensional CFT is known to be a localization of its 4K sphere. Yeah.
So do I understand correctly that what you did is that you wrote this theory for this beta field, and its solutions are going to be proper deformations that give me a Calabi-Yau deformation?
Exactly, yes.
It's like the equations of motion are exactly all the Murray-Cartan equations and different.
Absolutely, yes. That's that was in that was in this paper of BCLV from like '94, I think.
So you basically write physical theory for solving basically a purely mathematical question of deforming the geometry.
Well, you could say it's a purely mathematical question, but certainly, deforming the complex geometry is a piece of deforming all aspects of the geometry.
Yeah,
so,
of course.
But
I mean, I wouldn't know how to solve the deformation problem, I guess.
it's much easier than finding Ricci flat metrics.
Yeah.
I mean, locally there aren't any deformations. I mean, all Calabi-Yau threefolds are locally the same. So it's kind of a much easier problem. It's a question of patching.
How many supersymmetries does this serve?
The B model on this geometry has PSL 2/2 symmetry, which is a piece of the physical PSL 4/4.
And there are symmetries.
Yeah, there are symmetries. One of those two SL2s and PSL 2/2. And then there's eight fermionic generators, which are superconformal generators.